This is a very common type of energy conservation problem when it comes to springs. The first thing I like to do is draw out the scenario. And that just helps you associate certain numbers with certain visuals. So here we have a spring. We're making it horizontal because they didn't say anything about it hanging. So we know that that's 0.22 kilograms. We know it oscillates at 2 times per second. When they say per second, that should remind us of hertz. So that means our frequency is 2 hertz. Because if you don't know, hertz is the same thing as per second. It's unitless on the numerator, so it's just technically 1 over seconds. And we have an amplitude of 0.14 meters. So amplitude means the furthest it'll stretch out from the equilibrium on both sides. So it'll go this way, 0.14 meters, and that way, 0.14 meters. Cool. So now we're solving for V when it passes through the equilibrium point. In this case, we know that this has to be a conservation of energy equation. So I like to draw out the diagram. The conservation of energy. Draw out a before and after. So let's say the equilibrium point is our after. So let's do that first. After we are at the equilibrium point, so there's no compression or stretch. So that means our spring potential energy is 0. However, our kinetic energy should be at its maximum when it's through its equilibrium. That's because the total energy stays constant. And in our scenario, we only have kinetic energy or potential spring energy. There's no friction, there's no gravitational potential. So if there's no spring potential, that means our kinetic energy should be where all of the total energy is converted to. And vice versa, now we go to our initial state. Total energy stays the same. At the amplitudes, it should not be moving because it's changing directions. And that means all of our energy is stored in the spring potential energy, which also makes sense because the compression or expansion is at its maximum. So knowing this can help us write our conservation of energy equation. The spring potential initial equals the kinetic energy of the final. So let's expand that out. 1/2 kx squared equals 1/2 mv squared. Now we notice that the 1/2s cancel out, and then nothing else can cancel out. So we know that x can be substituted now at the amplitude, which is the 0.14, and then the mass is 0.22. Now here we see we don't know k. So to solve for the spring constant, we can use the frequency equation. So use spring frequency equation. That is actually 1 over 2 pi square root k over m. We can also take the period equation and invert it if that's what you've memorized instead. So the period equation, you just take the reciprocal of everything. So instead of 1 over 2 pi, you have just 2 pi, and then the fraction is inverted, so it's m over k. I mean, you can use either equation, but just make sure when you use the period one, you flip your answer at the end, so you take the reciprocal. Again, we don't need this at the moment, so let's solve for it. So that means 2 equals 1 over 2 pi with k over the mass, which is 0.22 kilograms. And 2 is in hertz. So k ends up becoming 34.7 newtons per meter. It's always a good habit to write out your units just so you're not confused. That can go in here. Now we plug in Chug. So 34.7 times 0.14 squared equals 0.22 v squared. And that should give us 1.76 meters per second.